Welcome back to MAT052. This time we're going to look at finding probabilities using area of rectangles. So this may sound kind of strange, but it comes in handy for doing other type of distributions. And then the method that we're going to kind of do, splitting things up, and the way we look at them will help for just continuous distributions, normal distributions, and other things in general. Okay, so let's get started. I know you've already talked about this in class, but what we basically do is represent probability as area. So we have a proportion of the area, the total area being 1, and then we're just going to do pieces of it, and that's the probability. So probabilities of continuous random variables may be represented as area under a curve called a probability density curve. So we looked at continuous random variables before where they could be between any two numbers. So it's going to be, we don't have precise probabilities of, individual numbers, and what we do is consider ranges between that we're going to kind of deal with. So here's some probability density curve. You can see that this is certainly skewed to the left, and we want to find some probability where here's our interval notation that we just covered. A less than or equal to X less than or equal to B, so this would be the A and B inclusive. And what I would like to do out of that probability is sum up all those probabilities. We're just basically adding, but how do we do this when we have a curve? Okay. So we're either going to have some table that gives us this curve's values. That's the normal distribution curve. But in many other cases that we can actually kind of work this thing through. Okay. So the area under the curve between two values A and B is the probability that a randomly selected individual from the population will have a value between A and B. So that's what that means. So if it falls, any of the random variable output value would be in there. Okay. So the area under the entire curve represents the entire population. That area is equal to 1. So what would be the probability if this is the smallest and that's the biggest? Well, certainly 1, because it's going to be within that range of the population. Okay, so reading this, we kind of did this when we were doing the empirical rule. So we would want to know, here's the 6895, almost all the 99.7. Here is a probability density curve, and they've given you values between certain ones. Okay, so, this is a continuous distribution, so we could have values 1, 1.5, and 2, but they've only given you the values for this thing. And the way this is laid out is that here's between 2 and 0, the probability between 2 and 0 is 0.3233. That area, everything is 1, and that's at almost a third of the area. Here's a little over a third between 2 and 4. The probability that something was in here would be 0.4386 between 4 and 2. And then the rest of the way out, there's no stopping point, so that means all the way over X greater than 4 would be 0.2381. And just like we did and broke down the empirical rule, so there was 68% between plus and minus 1, well, that was 34% less than between the mean and one standard deviation down, and then the mean and one standard deviation up, the 34%, the positive piece of it. So here's the values. Here's some questions that you could then be asked. What is the probability that X is greater than 4? That would be the 0.2381. That would be this interval here, and the area is given up under that curve as 0.2381, and that's the probability. So if I went through, and if I wrote this, I would say the probability that X is greater than 4 would be equal to 0.2381. That's how I would write that. What is the probability that X is greater than 2? Okay, so here's two different pieces of it. I've got this little piece in here between 2 and 4, and then above 4. So the probability of X greater than 2 would be the sum of these things, the 0.4386 plus, and I'm going to write it down here, so 0.2381, 7, 16, 7, and then 6. 0.6767 would be the probability. So I would add up this little piece of the area and then that little piece of the area. Okay. And we got this right, 0.2381 and the 0.6767. Okay. So if we have a uniform random variable, the uniform random variable would be between, let me slide this down a little bit more. So it would be between two different values, B and A. It would be uniform. The probability would be just, the same for anything. This would just almost like if we had the rolling a die, but that would be a discrete. It would be 1, 2, 3, 4, 5, 6. The probability would be 1/6 for each one. This is kind of the similar thing, but we need for this to be a good probability distribution. This needed to be an area equal to 1, area of a rectangle is equal to the length times the width. So that's what I'm going to do here. The length of this thing is just going to be B minus A. So this was 4 and this would 2. That would be a length of 2 in there. And now to make this be equal to 1 for a uniform, I'm just going to say if this is B minus A times the height must be equal to 1 for everything in here, the length times the width of everything, then my height must be equal to 1 over B minus A, which is what this is. That's how they got that, okay? When a random variable is uniformly distributed between two numbers A and B, the probability density curve is a horizontal line with value 1 over B minus A between those two intervals, okay? So a probability event for a uniform random variable is represented by an area under the line, which forms a rectangle. Therefore, to find the probability of an event, we simply calculate the area of the appropriate rectangle. So we find whatever piece of it that we need to know, and then we just basically do a length that, and then the height of the uniform. So the time it takes for a certain elevator to arrive on the ground floor once the call button is pushed is uniformly distributed between 0 and 40 seconds. Okay, it could be any time between here, a person may come and hit it, and then it may be already on the ground floor, or it may be up at the top, and anywhere in here in between, just equally likely to be anywhere in between there. So a person pushes the call button for the elevator at a randomly selected time. What is the probability that the elevator will take less than 30 seconds to arrive? Okay, so here we want to know, here's our uniform distribution. It could go between 0 and 40. The width being 40 minus 0 is 40 times 1 over 40. So 40 times the 1 over 40. This area is 1. Okay, but what we're asking for is what is the probability that the elevator will take less than 30 seconds. So here is this piece in here. And what we need to do is calculate the area over on the side. Okay, so now the height is still 1 over 40, but the width, this in here, between here and here, is 30 minus 0 is 30, okay? So the area in here, or the probability that x is less than 30 is equal to 30 times 1 over 40 is equal to 3/4 or 0.75. That just happens to work out, very nice. Okay. So there's the picture. Here's the area that we needed. And to find that probability, we just calculated that from just basic area, okay? 30 times 1 over 40, that's the 0.75. So the probability that the elevator will take less than 30 seconds to arrive is 0.75. Now, I want to point out something. Notice that this could be less than 30 seconds or actually less than or equal to 30 seconds. When I've got Sorry. Get back here. When I've got a continuous distribution, to have the difference between having less than 30 or less than or equal to 30, the probability is going to be the same thing. You're not, when we're doing area, and if we've only got like this one little line in here, there's no area under there. So when I'm dealing with continuous, if I actually said what's the probability that x is exactly equal to 30, it would be 0. We can't do that. We would have to say between 29 and 31, for that. Okay. So that was kind of the notes for that. And then we continue. In an automotive process, the paint is applied in several layers. The thickness of the paint is uniformly distributed between 90 and 110 microns. So notice that this width between there and there is 110 minus 90 is 20. The 20 microns. And then I want this area, the total area in here is 1, because it's uniformly distributed. And in order to have the height, the width 20h, 20 times 8, the length times the width to be equal to 1, the unit area, h is equal to 1 over 20, and that's where this comes from. Okay, so we know this is 1/20th. But that's where they got it from. We know it because it's labeled. Okay. So what is the probability that the paint thickness will be between 100 and 105? So I've got a line here between 100, 105. 105 minus 100 is 5. I know the height is 120, so the area in here is the 1/20th times 5. 5 over 20, the 1/4. Okay, so there's the little curve in here. This is the area that we want to find. The width is 5. The height is 120, so that is just 0.25. The probability that 100 less than, let me see how that, between 100 and 105 microns is equal to 0.25. And this is the same thing if we just had that less than or equal to. Those inclusive and exclusive for this probabilities are going to be the very same thing. Okay. So here's your practice problems. These are laid out. Here's a curve. Here's the area under the curve, and then they're going to ask you these different questions. Write your answers using the probability notation, and then do your answer over to the right. So that way we know how to write this, what this interval means, and then how to calculate the probabilities. Okay, so take a look at those. Get your answers and submit those for me, and we'll see you next time.